Our speaker today is Elitsa Hadzhiivanova. Elitsa completed her master's studies at our Department of Marine Geosciences at the University of Haifa under supervision of Dr. Nicholas Waldman and Dr. Rita Gutman. Elitsa was born in Bulgaria. She completed her bachelor's degree in geophysics, Department of Geophysics and Planetary Sciences at the Tel Aviv University. Elitsa actively participated in the Dead Sea deep drilling project since 2010, and her research interests are mass wasting events and limnogeology. Please.
Hi everyone, thank you for coming. This is the subject of my thesis, Sedimentological Insights into Depositional Events in the Dead Sea. It's part of a bigger project, the ICDP Dead Sea Deep Drilling Project. Let's go over the table of contents of today's talk. First, I'll give an introduction about the tectonolacustral basins and concepts in mass wasting and mass flow. Then I'll talk a bit about the regional setting of the Dead Sea, my hypothesis, research objectives. We'll go over the methods and materials, results and discussion, and then we'll finish with a summary and conclusions. First of all, tectonolacustral basins. Here are some examples, such as Lake Cami, Lago Faniano, which is in Patagonia, Lake Tanganyika, and Lake Baikal. Those are tectonolacustral basins. They form either in rift basins or strike-slip margins, and they're usually characterized by a flat lake floor, elongated basins, and very steep slopes. And because the slopes are very steep and those are tectonic basins, there's a high potential for mass wasting. Mass wasting is often triggered by earthquakes from the lake slope. This is a hypothetical example. The slope doesn't even need to be that steep. A mass of sediment glides down the slope. It overwent some deformation, then it's transported further and then suspended in the lake water. By the time we get some distal turbidite, the sediment is completely suspended, and it's a mass flow which is later deposited again. So let's talk a bit about sediment flow and deposition. Sediments behave according to their grain size. There's a settling velocity typical for every grain size. Clays, in order to be deposited, need the settling velocity to be effectively zero, whereas coarse sediments can be deposited at much higher velocities. Basically, there are two phases of mass wasting, mass flow. There's a debris, which can further be mixed with water, turn into a turbidite, and both of these flows can exist simultaneously. Also, turbidites can slow down to become debris again, and vice versa, depending on the conditions. In short, we have sediment and a fluid. We mix them together, and under the gravity forces, we create a flow, which is a different material. It acts as a different material. If the density of the flow is lower than the density of the particles, we would have normal grading in the sediment, which is deposited by this flow. And if the case is the opposite, the density of the flow is higher than the density of the particles, which could exist in the breeze, for example, we have reverse grading. Now let's talk a bit about the basin, the Dead Sea Basin. It has been extensively studied in the exposed outcrops. The Dead Sea Basin consists of a deep basin and a marginal environment. It had been divided by previous authors into several depositional environments, but for us it is more convenient to use these parts as the deep basin and the exposed outcrops as the marginal environment. The Dead Sea Basin is a tectonolacustrine basin, which is the biggest pull-apart basin on the Dead Sea transform system, which separates the Arabian plate from the Sinai plate. It's an endorheic basin. It's an endorheic lake, which means that everything that comes in from the watershed remains in the basin, apart from brines, which can protrude through the bedrock and can carry some solubles. But all the sediment that comes from the drainage area would eventually be deposited here in the basin. And thus, for thousands of years, we have accumulated the Dead Sea group, which consists of the thick evaporite sequence, the Sedom formation, the Amura formation is lacustrine formation, the Samra, Lisan, and Tselim. Those are the lacustrine formations of the Dead Sea group. This image is being updated all the time. The thickness of the formations is being updated according to new studies all the time, and the ages as well. Now most of the sediment gets to the Dead Sea through flash floods. Those in modern days, those occur mostly during the winter season, and those floods carry sediment, which is then mixed with the lake waters and slowly deposited. Now, in 2010, began the ICTP drilling project, which continued up until March 2011, and those sediment cores and many more were recovered. I took part in this project, and later when I did some of the core descriptions, I noticed that not only do we have laminated sequences, but we also have these. Now, laminated sequences are the steady state sediment, which means that we have detrital laminae, where a flash flood deposited its sediment. The detrital lamina is the dark lamina. And we have also pale laminae, which is chemical sediment, chemical deposits from lake waters, which are deposited during dry periods. Now we can get seasonal laminae, or there are debates whether these are seasonal or not, but we also have these deposits which don't seem to be seasonal. They appear very much like mass wasting deposits in other environments which we've seen, and I suspect them as mass wasting MTDs, mass transport deposits, or mass wasting deposits. I called these layers, the thick layers, large-scale detrital layers. And in order to study them more extensively and to really find out whether these are mass wasting deposits or not, I had to characterize the sediment in the deep basin, also characterize the sediment in the marginal environment, and compare these two, because I would expect that a mass transport deposit originated somewhere on the lake slope or in the marginal environment and was then deposited in the deep basin environment. And of course, after I study both the sediment in the marginal and the deep basin environment, I would have to propose a source-to-sink mechanism for these MTDs, mass transport deposits. Now, as I mentioned earlier, the materials for this project were provided by the ICDP Dead Sea Deep Drilling Project. We have maximal depth at site 1, which is here in the middle of the lake, of 460 meters. Now, I only sampled site 1. We additionally have site 2 and 3, which are nearer to the lake shore. But I was interested in the deep basin, so I sampled site 1, and I sampled in the orange intervals here, which were constrained within a known age. We had some preliminary radiocarbon dating, so I knew what the ages of these intervals were, and I also knew that this is high stand of the lake and this is low stand. And these here are low stand again. Additionally, in order to study the spatial distribution of sediment in the marginal environment, I studied two sites, site A and site B, which is downstream. This is a gully at the Tselin floodplain, one of the gullies. These sites are set 80 meters apart in the east-west direction, and basically we moved downstream from west to east. Now, the methods I used: well logs were obtained from the deep basin environment, from the ICDP core. Those logs contain magnetic susceptibility data, gamma ray data, radiocarbon dating for some of the organic fragments which were found in the cores. Those were not conducted by me, but by Professor Kitagawa from Nagoya University in Japan. Those ages are available for participants in the project. And also I have core log data, which is obtained by an MSCL, which is a multi-sensor core logger, and we measured magnetic susceptibility, which tells you something about the behavior of sediment when a magnetic field is induced, and also X-ray fluorescence, which gives you some information about the geochemistry of the sediment. XRF was conducted at low resolution for all the core sections and at higher resolution for only a few chosen core sections. Now, I also did lots of grain size measurements, granulometry, for chosen intervals, mostly large-scale detrital layers. And I also had some mineralogy analysis using a qualitative X-ray diffraction. And in order to see the crystals themselves, I wanted to create some smear slides in order to see their size and how rounded they are. I also used the Rocky-Powell method, which is a method for estimating the total organic carbon content, the TOC, which hadn't been done before in the Dead Sea. Now I'll show you just some of the results. This here is an age depth model created using the radiocarbon ages from Kitagawa. We see that in the Holocene interval, We know that this is Holocene because it's about 13,000 years, and those points fall pretty much on the same line. But in the Pleistocene period, those dots don't fall on the same line, but rather between two lines. And all this was used to give some average deposition rate, which is the slope of the line. So in the Holocene, the average deposition rate of the sediment is about 6.6 millimeters per year, and in the Pleistocene it's about 1.4 millimeters per year. Now let's talk about the stratigraphy of the deep basin. I did some core descriptions from images and created this columnar section of the 460 meter core in site 1. I also applied some log data here and used it to divide this columnar section into 4 major units. Now, the boundary between Unit 1 and Unit 2 can be seen more easily from the gamma ray data, but the boundary between Unit 3 and 4 is more prominent in the magnetic susceptibility data. Unit 1 consists mainly of evaporites and some detritus and laminated detritus, also known from previous works as AAD, which is alternating aragonite and detritus. Aragonite is the pale laminae, detritus is the dark laminae, basically laminated sequences. Unit 2 consists of a lot of disturbed sediment, which has some internal structures such as laminae, and it has less evaporites, mostly gypsum. Well, it mostly consists of detritus and laminated detritus, but it has some gypsum instead of salts such as halite. And Unit 3 is more similar to Unit 1. It has some evaporites and also lots of detritus. Unit 4 also has some evaporites, but also the disturbed layers, the deformed sequences of laminae and detritus and evaporites alternating all along the unit. Now, the stratigraphy of the marginal environment. This is the site that Revital Bookman worked on in the past. So I know the radiocarbon ages for this site. Those ages correspond to 390 BC and 31 BC. I used this interval here, which consists of 2 laminated sequences and detrital layers in between. And there's one at the base, which I didn't work on. That's it. Now, I made an attempt using those radiocarbon ages to correlate between the marginal environment and the deep basin core. This is site A, which is nearer to the lake shore, and this is site B, which is downstream at the Tselim Gully, and this is from the deep basin core. And I took 2 ages from deep basin core and constrained this interval, and this core section fitted best the stratigraphy that we see here. And we already see that some of the detrital layers are much thicker in the deep basin environment. So it has to do something with a special depositional mechanism. Now, the laminated sequences, they're very uniform in mineralogy, usually consisting of very fine sediment, fine silt, and some quartz sand, but mainly carbonates, and clays and quartz. Now it's more convenient to look first at the first group, at the uppermost sequence, and then the lowermost sequence. I sampled the same lamina at the two sites, and the blue curve is at site A, the red curve is at site B downstream, and we see in all four examples, those are examples of four different tritolaminae. We see that there's some dynamic sieving downstream, which we would expect usually in such environments as a fluvial environment. We would expect sediment to become thinner as the flood progresses towards the lake. In the lower sequence, we see a similar trend, but it's much less prominent, which means that the floods probably had higher energy and were able to support larger particles and carry them further towards the lake. Now, the chemistry of laminated sequences. Laminated sequences consist of, as we said, the tritolaminae and some calcitic laminae or aragonite laminae, some calcium carbonate laminae, where the calcium is peaking. Calcium is the dominant component along the core, along all the cores, all the sediment in the Dead Sea. However, we have some terrestrial allochthonous material, which is typifying the dark laminae. And there are some elements such as sulfur and chlorine, which are independent of dark and pale laminae. Other characteristics. We also have some organic remains embedded in laminated sequences. In general, we have plenty of organic remains embedded in sediment in the marginal environment, which is good for us because we can use it for dating. Now about the sequences that are not laminated in the marginal environment, we have these massive units, which are basically uniform and massive, and we have similar units which, however, have some internal layers. We have mixed layers which have been described by some works such as Marco, 1996, and we also have seismides, which both mixed layers and seismides are associated with seismic events and mixing of the sediment as a result of seismic events. However, these have not been extensively studied, and the origin of those was not proposed yet. We have several detrital units, detrital layers, with the first two types in the marginal environment. And this is the sampling resolution at which I sampled these units in order to obtain some grain size measurements. And these are the grain size measurements I have. Basically, we see that this layer is interlayered. Some layers are coarser, some layers are finer. And here we have a layer which shows some reverse grading. Now, that reverse grading is not seen in the outcrop downstream, but we also see again that this layer, this unit, is interlayered. Now, in the deep basin environment, we also have the massive detrital units. We have the interlayered units, but we also have something which appears to be graded. And in addition, we have some deformed units with a different degree of deformation, from the formations in which the internal structures are preserved to breccia. So I chose to sample these intervals from Unit 1, Unit 2, and Unit 3. Those are the sequences, and in orange is indicated the detrital layer, which I sampled for grain size measurements. On total, 250 samples. Now, I did the measurements twice, once without dissolving the carbonates, and the second time after dissolving the carbonates. This is a typical detrital layer from Unit 1. It consists of relatively uniform sediment. It appears to be uniform, but there's some normal grading towards the base. There's a coarser layer on top. In the XRF measurements, we don't see anything we don't see a specific pattern in those layers. Each one is different, each one behaves differently from the other. And this is a similar layer, but this time from Unit 2, and we see that the grading is much more prominent at the base, and we see that the coarse material is somewhere some 1 centimeter above the base of this layer, if we say that the layer is constrained between two laminated intervals. Now again we see that the XRF data shows some trends in the laminated intervals, but doesn't show any specific signal in the non-laminated interval. Now this is a layer from Unit 3, which is similar to the previous. Some coarse material at the base and basically normal grading. I did some total organic carbon measurements on this layer, and it doesn't show anything specific, at least at this point. Now I also did some X-ray diffraction measurements of the tridal layers, and I found that they were pretty much very uniform. The detrital layers consist mostly of phyllosilicates, which is predominantly clays, and bicalcite and quartz. And in some cases, the dominant component is gypsum, which is the case where the sediment is sandy and contains lots of quartz sand. Now, gypsum is usually either hexagonal, like this, or lenticular. The lenticular crystals usually occupy pores between bigger sandy particles, while these are seen all along the core. This is the predominant picture from the entire core. Very fine sediment, consisting mostly of calcite, quartz, and aragonite, and occasionally we see some feldspars and some tellurica, some algae, microscopic algae. We have two types of quartz. We have the very rounded grains of quartz, which probably have their origin in desert dust, and we also have a less rounded quartz, which probably originated from some siliclastic rocks in the area. Now again here we see the only special trend of TLC is when the TLC diminishes if the sediment is coarse. if the sediment is sandy, there's less TOC. And that was the only trend that I noticed. Probably because sandy sediment cannot support much organic matter, it probably migrated towards other sediments. And the TLC ranges between 0.02 and 1.5%, which at the moment doesn't mean anything. I'll discuss it later. Now, I used the log data from the Deep Basin core, and I applied this Delta 018 data, which is from Barmatius 2003, and I compared between the two. This was earlier correlated to the Dead Sea group, so I knew that this is a Tselim formation, the Lisan formation, Samra, and the Mora. And here I knew some of the ages using radiocarbon dating, so I already knew that Unit 1 is Tselim and Unit 2 is Lisan. And I saw that the data 018 trend is pretty much opposite to the gamma ray trend, and I used that to correlate between the other two units, and I realized that this is Samra and this is Amora. So now that we know that this is low stand and this is high stand, and low stand again and high stand again, we see that during more humid intervals we have more sand because the gamma ray is more steady, so the detritus which comes from the drainage area is more sandy, whereas here it's more clay. And the same trend here and here. And in the magnetic susceptibility, we see that during drier conditions, we have more paramagnetic minerals, such as clays, which increase the magnetic susceptibility, whereas in humid periods, we have more calcite and quartz, which decrease the magnetic susceptibility. So now let's compare the deposition rate to some previous works. We had 6.6 millimeters per year in the Deep Basin, and we can compare that to the marginal depositional environment, and we see that in the Deep Basin the rate is higher, and the same for the Lisan formation. In short, we see two trends. During more dry conditions, during a low stand, we see that the deposition rate is higher, and during high stand it's lower. And also we see that in the Deep Basin the deposition rate is higher than in the marginal environment. The reason that the deposition rate is higher in low stands is because we have a smaller lake volume, and thus we can distribute the sediment over a small area, whereas during high stands we have a large area to cover with pretty much the same amount of sediment. Now we can see that in laminated sediments, this is a comparison between Lisan lamini and Tselim lamini, and we see that Tselim lamini are much thicker than the Lisan lamini. This is a comparison between the Deep Basin environment and the marginal environment. We see that there is no There's no apparent difference between the thickness of laminae in the deep basin and the exposed outcrop. Therefore, something else is increasing the deposition rate in the deep basin and not the deposition of laminae. This is just a summary. We see that downstream the grain size decreases in the detrital layers, which probably have their origin in floods, flash floods, or mass floods. And we see a similar trend in the detrital laminae. The grain size decreases downstream. Now the TOC, which is less than 1.5%, is actually very low in comparison to other oligotrophic lakes. This is Lake Baikal and this is Lake Tanganyika. They're both oligotrophic lakes, and the deposition rate there is much lower, but the TOC percentages are similar. So we can say that the Dead Sea has very little TOC, at least in the deep basin environment. This can be a result of organic matter supply. Maybe most of the organic material is concentrated around the margins because it consists mostly of macrophytes, which are floating on the water and can be pushed by wind towards the shore. Or it also could be because of organic matter preservation or sulfate reduction, which can destroy the TOC, which can destroy organic matter, and basically we don't have as much TOC. Now, in the low-standing formations, we have this trend of detrital layers. We have some normal grading. The coarser material is concentrated a few centimeters above the base of the layer, and here we have either reverse grading or no grading whatsoever. This is basically a turbidite deposit, and the reverse grading is the result of some erosion of the lake floor sediment, and also the result of a slowing down of the turbidite because of friction. And in the high standing formations, we also see, additionally to this, we see this kind of deposits, which are deformed sediments, and they don't exist in the low stand formations, Samra and Tseli. Now, I'm going to talk about the seismic trigger of mass wasting deposits, mass wasting events and deposits. We have, there have been some works done on the seismic record of the Dead Sea. Some sediments such as seismites were used for this record. They were dated, and thus we have a record which goes back as much as 70,000 years. And Marco published this, which is a 50,000 year paleo earthquake record of the Dead Sea Graben, an earthquake clustering. And this is a similar work on the Holocene by Migowski, and I can say that we have here a clustering of mass wasting events, because I used my deposition rates obtained from the H-depth model, and I applied them I calculated them by the depth here. By the ages, and I got the depth, and I see in this interval very many mass wasting deposits, and I cannot separate them from each other. Like if it's 71,000 years BP, I cannot say if it's in the core, if it's here or it's 1 meter further, because it's really a clustering of these events. And I have, however, some specific events, like this deposit here, where an organic remain was found. It was dated to a specific date, and this date corresponds to an earthquake event from the paleoseismicity record. And I have 8 such events. Now you can see that none of these events is represented by a deformed layer. They're all very mixed, and none of them is this type. In fact, none of the organic remains which were found in the Deep Basin core was found in layers of this type. And if we assume that most of the organic material is concentrated around the lake shores, we can say that this is a local event for the Deep Basin, whereas these are the distal mass wasting events. And those events are not only local for the Deep Basin, they're also local for the marginal environment. Alsop and Marco published this work, the so-called seismoids, which also have some element of flow. Those are slumps which form on very low gradient surfaces. And Marco and Alsop proposed that they were triggered by earthquakes. Now, I guess there is not only the earthquake trigger, but also some climatic trigger of mass wasting. And for example, this could be overburden of the lake slope. During low stands, we have very high deposition rates near the lake slope. And this could cause some changes in the hydrostatic pressure and make the sediment near the lake slope more susceptible to mass wasting. So if we have, for example, a very intensified rain or other event, we can have some mass wasting because of a flood which goes through those areas with high accumulation. In the high stand, however, we also have the detrital layers, but we also have the deformations, and we need to study them more extensively and see their spatial distribution, which we lack in the Deep Basin core, and see if those are really low gradient slumps. So to summarize, the Deep Basin depositional environment has deposition rates of 1.4 and 1.7 times those in the marginal environment, which means that we have some mass wasting mechanism which brings sediment from the shallower parts of the basin to the deeper parts of the basin. The detrital layers in the Tselin Formation marginal environment are much thinner than their counterparts in the Deep Basin, which basically means the same. There are some The deep basin is the depot center. Most of the sediment which glides down from the lake slopes would be accumulated there. Also, other detrital layers are local events, such as those deformed units, and they can be only observed in the marginal environment or the deep basin environment. The stratigraphy of the deep basin environment, Lisan-Namora Formation, comprises mass flow deposits of slumps, turbidites, debris with the opposite grading pattern, the reverse grading pattern. In the formations Tselim and Samra, there are mostly turbidites and some debris. There are also some breccias, but we don't see the deformed slump deposits. And I can also assume that the main mechanism of organic matter deposition to the deep basin is mass wasting, because all of the organic remains found in the deep basin environment were found in layers which are represented by mass wasting events. And that's it. Thank you.
Thank you very much, Elitsa. Any questions, please? Yes, please.
Yeah. I have two questions actually. The first one is you have to be careful when you, in one of your last slide, you showed a sequence that you interpreted as a MTD or this one. Oh.
This one?
Yeah. And it may also be the result of seismic checking.
It is. It is a Kelvin-Helmholtz instability, but it also has a flow element to it.
You have a flow. It's not clear. And the other, my other question is, I don't understand how you discriminate between in your deposit between classic turbidites and hyperpyknites, which are gravity flows triggered by the flood. And it is not clear for me which criteria you...
I can't distinguish at this stage between the two, and I can't also...
Did you try to make a detailed grain size analysis, but within one, within single deposits?
Yes.
What do you mean, single deposits?
Between the... Can you show again your grain size deposit curve?
She shows it.
This one? No. Which one? I can't say at this stage what kind of flow it is, whether it was triggered by earthquake or by a mass flood, because I can't really distinguish.
Okay, other questions? Yes, please.
You raised some interesting questions regarding the organic matter. You used Rockval, but you presented, if I'm not mistaken, only the TOC out of the Rockval data. The oxygen index or hydrogen index or any other aspects of the Rockval, did they tell you any of the story? Because they might answer some of your questions.
I had some very complex curves when I used the Rockval, and I need to use some decomposition to separate those curves into other curves, and so they can tell me the story of what kind of vegetation there was or the other parameters. They were a bit complex and I didn't have time to analyze them, but I guess in the future when I analyze more samples I'll do that more extensively.
I'd like to see that if you want somebody else to
Okay.
have a look.
Okay.
Okay, you showed a bunch of gypsum crystals from your smear slot, and you have at least two morphologies. You have the hexagonal and the lenticular. Do you have twinning in the lenticular?
No.
Okay, have you looked at the ratio between the form of the gypsum is dependent, among other things, on the accompanying pH and type of organic molecules available. And have you looked at the grain morphology or the ratio between the lenticular and the hexagonal? And if you looked, have you looked at the ratio at the distribution of those relative to your organic matter content?
No, but actually, this is a good example. There's some gypsum here, and you can see how the organic, the total organic carbon diminishes.
Okay,
But this is mostly the lenticular gypsum.
that's mostly the lenticular gypsum, and that
Yes.
and the hexagonal gypsum occurs where?
Pretty much everywhere it can be seen independently.
So the hexagonal is the normal background, and the lenticular is the
Yeah.
exception.
The lenticular is mostly found within sandy sediments.
Oh, that's interesting.
Okay, other question?
Just before we finish, can you show again the age correlation slide? That's the. I mean, there was a slide where you had the
age model.
age model.
The edge depth model. There will be a model which would be published by one of the PIs for the ICDP. This is the one I used in my thesis because there was no model published yet, but when I publish a paper, I'll probably use the model which was the universal model for this
What I
data.
wanted to see is that you made a distinction between high stand and low stand, and I wanted to see that again.
Yes.
There was a slide that actually showed that what is high stand, what is low stand, or your correlation of the material with the high stand and low stand. So this is a more lower. This is a lower resolution.
Okay.
Yeah,
What do you
low
mean?
stand.
You have a slide with small standard higher pH.
That's the thing. It's not really a high stand. It's rising from 18 to 6.
It's a lake. So
It's the lake stand. Yeah.
Do you mean this here? This is only a distinction. I'm only distinguishing between Lisan and Selim, and this is a falling stage, I would say, because I only sampled the top of that sample page.
Usually on the center.
Okay, maybe you will ask later specifically your questions. Okay, I see that there is no questions. Thank you very much, Elitsa.